Good evening, how are you? It's GoPro Flying here, and welcome back to another video. And today I'd like to show you a bit of a video regarding a very useful piece of kit that's used for flight training. It's used a lot for the private pilot's license and through the commercial pilot's license and all the way up to the instrument rating. And it's a device that you'll use an awful lot during your private pilot's license and also a hell of a lot in your ATPL ground school. And it is called the navigation computer. And the navigation computer has multiple names. In the UK there are different types. You've got the CRP-1, the CRP-4, the CRP-5, the CRP-9. You've also got things called the E6B, and you've got multiple other versions as well, which all effectively do the same thing. So this is what it looks like. It's effectively a piece of plastic. This is obviously a digital version, which I managed to get my hands on, which is very convenient. And on one side you've got what we call the wind side, which allows you to calculate things like drift, headings and tracks. It also allows you to calculate the wind velocity itself if you know the heading and track. And on the other side we've got, if I just find it, and on the other side we've got this side, which is the what we call the computer side, which allows you to calculate a multitude of different things and do lots of conversions and calculations, and we'll come back to that in a minute. Now the purpose of this video is not to show you how to use it. This is just an introduction to show you what it is and effectively what it can do. And over the next few months I plan to make many videos on how to use each and every individual part of the CRP-5 which this specific digital model is based on, with worked examples, so you all know exactly what you're doing and how to use it. So what I'm going to do is start off on the wind side, and I'm just going to give you a quick introduction as to what it is, what everything does, and why we use it. Well, first thing to know, we've got this rotating bezel on the outside, and this rotating bezel, as you can see, is basically a compass rose. We've got the cardinal points, north, east, south and west. We've also got the four quadrantal points, north, east, southwest and northwest. And this whole outer bezel rotates. Now within this outer bezel you'll see there's a transparent window. On the real CRP-5 this is a plastic window of sorts which you can draw on. You can put pencil marks on it, you can put pen marks on it. They are going to be replicated on this digital version by this red cross, which I can move around and drag about and put it wherever I want. And obviously as I turn this dial you can see that the pencil mark, as it would be, rotates with the device, which is very useful. On the back we have this sliding scale. It's just known as basically the slide, I think. I have no idea, that's what I call it. And you can see on the back of it you've got all these numbers. Now the numbers on what we call the low speed side, if you look down here, we've got low speed and high speed. I'll get to that in a second. So on the low speed side you've got numbers ranging from 40 knots all the way up to 300 knots at the top. And left to right you'll see we've got these fan lines which diverge as we go to higher and higher speeds, and these replicate the amount of drift that an aircraft can experience based on a certain amount of wind that is present. And as you can see, the amount of drift in numbers of degrees left or right of the center, that is 10 degrees right, 20 degrees right, etc. The number of degrees of drift decreases as the airspeed increases. You can see here that the maximum amount of drift we can really attain is about 15 degrees, just under, whereas we go down here to very low speeds, 50, 60, 70 knots, the maximum amount of drift can be, as you can see, upwards of 30, 40, even 50, 55 degrees. And that's simply because the amount of drift that an aircraft experiences decreases as the airspeed increases. So this on the back here is your TAS, your true airspeed, and we've got degrees of drift left and right. On the top of the CRP-5 you'll notice there's a sign saying true heading. That's the aim of the goal, is to figure out your true heading, put that under there, and then from that you can work out what your magnetic heading is by applying easterly and westerly variation accordingly. Again, I'll show you that in another video, exactly how to do that. On the bottom of the CRP-5 we have this big square section here, And this big square section at the bottom of the low speed slide is used to calculate headwinds, crosswinds and tailwinds. So if you want to know on a given runway with a given wind, what is your maximum crosswind, or what is your crosswind, what is your headwind, what is your tailwind component, it allows you to split your wind up into vertical and horizontal components to give you, as I say, headwind, tailwind and crosswinds depending upon the strength of the wind, the direction of the wind and the direction of the runway that you happen to be using. If we switch over to the high speed side, the only difference is that the scale changes. So we go from one side where we said the airspeed goes from 40 to 300 knots. On the high speed side it goes from 150 all the way up to 1050 knots. And again you can see that the fan lines diverge as we go to higher airspeeds due to the fact that the amount of drift an aircraft can experience at higher airspeeds decreases. So at very high speeds, over 1000 knots, you're looking at 10 degrees drift, whereas if we go right down to much slower speeds, 150, 200, again we've got drifts up to and just about exceeding 40, 50 degrees. That's about all you need to know for the wind side. It's a very, very useful tool, and anyone that's done any form of flight training will be more than familiar with it. Very, very useful. This allows you to calculate one of four things on this side. Number one, it allows you to calculate your ground speed with a known true airspeed, and it also allows you to calculate your true heading, which you can then convert into a magnetic heading if you know the variation. It allows you to work out what your ground speed and your track is if you know what the heading and the true airspeed is, and it also allows you to actually calculate what the existing wind condition is if you know your heading, your true airspeed, your track and your ground speed. And as I said earlier, you can also work out headwind, tailwind and crosswind components using this area at the bottom of the slide. On the other side we have the busy side. This is the computer side. This is a fairly complex side, and it is effectively a circular slide rule. That's all it is. It's just a circular slide rule from anyone who was born back in the, I don't know, 50s, 60s, before the age of pocket calculators. When you were at school you had to use slide rules to do calculations. This is exactly what this is, put in a convenient, compact, circular form. What it allows us to do is many, many things. I'll pick out the easy ones first of all. At the bottom we've got this section here which allows you to convert Celsius to degrees Fahrenheit. So you've just got this scale. Again, there's nothing you need to particularly know how to use. You simply just find out what your temperature in degrees Celsius is, and then you can just use the scale on the bottom to convert that into degrees Fahrenheit, or vice versa. There's also an equation you can use to convert Celsius to Fahrenheit, and I'll show you that when we start doing some calculations. What else can we do? Well, what else we can also do is, oops, sorry, let's move that out of the way. On the outer scale, we've got numbers of words. We've got a number of things written in red. You can see here we've got kilometers, meters, yards, statute miles, nautical miles, and feet. So this tells us that the outer scale can be used to compare distances. And on the inner scale, you can see this inner scale rotates. We can line up distances on the outer scale with times on the inner scale. Notice here how we've got the word hours, and over here we've got the word minutes. So we can actually line up distances on an outer scale with time in minutes and hours on the inner scale, and we can work out speeds. So we can use this as a speed, distance, time calculator to work out any one of the three variables. We can also use this to work out specific gravities. You can see here we've got specific gravities between 0.7 to 0.95. This is to calculate masses in pounds. And over here we've got this other arc which allows us, knowing a specific gravity from, again, 0.775, 0.885 and 0.9, we can use the specific gravities to take a volume and turn it into a mass, because obviously aviation fuel is lighter than water, so the ratio of 1 litre of water to 1 kilogram doesn't work for aviation fuel, but it does if we know the specific gravity. So we can use the CRP-5 to calculate masses of fuel quantities, which is very useful. What else have we got? Let's see. Specific gravity is pounds, kilos. We've got our distances on the outer scale. Notice we've also on the outer scale, sorry, I'll move that out of the way. I'll spin this upside down so you can see it. We've got the word TAS on the outer scale. Now TAS means true airspeed. So we've got true airspeed on the outer scale, and notice here on the inner scale we've got the word RAS. Now RAS is your rectified airspeed, also known as a calibrated airspeed, which for certain aircraft can be argued to be the same as your indicated airspeed. So we can use this inner scale with a known calibrated airspeed or an indicated airspeed, as it is for some aircraft, or your rectified airspeed for slightly more advanced aircraft, and we can work out our true airspeed if we know a number of factors. Those factors will be your pressure, altitude and the air temperature. So on the inner scale we have this window, we have a multitude of windows actually. We actually have 4 windows, this one here, this one here, this one here and this one here. They're all labelled so you know which one does what. And you can see on the airspeed window, it tells us here in a small box, this airspeed window is used to compute TAS from Mach number or RAS. So if I know the Mach number of my aircraft, I can actually calculate the true airspeed by using this window, and I can also use this window if I know my rectified airspeed. So I put the pressure altitude in here, this is in thousands of feet, and my air temperature in degrees Celsius, and then I can read off my true airspeed on the outer scale if I know my RAS or my Mach number on the inner scale. Note we've got this big red arrow here which points to, as it says there, Mach number or pressure altitude. One of the ways you can do this to calculate a true airspeed or a Mach number is simply by knowing the temperature. Again, this video isn't designed to show you how to use it as such, but I'll just give you a quick example. If I know the temperature is, let's say, minus 40 degrees, and I want to know what the Mach number is, what the local speed of sound is, you'll see that if I turn this upside down, in the airspeed window, you'll see this thing here called Mach number index. And what I can do is I can line up that Mach number index with a known temperature, let's call it minus 40, and then all I have to do is look for where this red arrow is, and it will tell me exactly what the local speed of sound is. And in this case, the local speed of sound under the 10 is just under 600 knots. So there's 500, 550, 560, 70, 80, 90, 595 knots if the temperature is minus 40. And that's because the local speed of sound is dependent only upon the temperature of the air, because the temperature of the air affects the density of it, and hence the speed of sound. So that's one thing you can do. And again, if you know your Mach number, let's say you're cruising at Mach 0.75, what is your true airspeed? Well, all you have to do is say, well, Mach 0.75. Again, on the inner scale, you've got your Mach numbers. So this is Mach 0.6, 0.7, 0.8, 0.9. So Mach 0.75 would be 1, 2, 3, 4, 5. And you can see there that the true airspeed would be about 445 knots at Mach 0.75, assuming the temperature was minus 40. What else have we got? We've got lots of conversions on here, so I can convert volumes. Again, I've got litres there, and notice I've got US gallons and imperial gallons down here. So I can simply line up a certain amount of a quantity of a liquid, for example. Obviously it's going to be aviation fuel, and I can say, for example, if I have 4.5 well, let's go for 4.5 US gallons, why not, 4.5 US gallons, so there's, or 45 US gallons, and I line it up against this small arrow here, and I can convert that directly into imperial gallons, or I can spin this upside down and then read off exactly how many litres that would be equivalent to there. The thing you've got to be very careful with the CRP-5 is the CRP-5, unlike a calculator, won't give you an exact answer. It will give you a value that is potentially many orders of magnitude out. So you have to be aware of your conversion factors to start with before you can use it effectively. What else have we got? So that's the airspeed window. And then we've got an altitude window here, which does very similar things. The altitude window is used to calculate true altitudes. We've got an airspeed window here, which we said we can use to work out a number of things. The airspeed window can also be used to calculate density altitudes as well. So you can put your pressure altitude and your temperature into here, and you can read off your density altitude in this window here. It's nice and straightforward. Again, I'll just give you a quick example. We'll do some worked examples in another video. But let's suppose, I might have to turn this whole thing upside down. There we go. So let's say we've got it's 0 degrees, and it's let's say we're at 10,000 feet. Okay, now at 10,000 feet, the temperature should be what should it be at 10,000 feet? It's 15 at the surface, 2 degrees per 1,000 feet. So 2 times 10 is 20. 15 minus 20 is minus 5. So we're going to say the temperature is 0, so it's warmer than it should be. So we're expecting a density altitude to be slightly higher than it actually is. And if you can see there, we've got our pressure altitude set up to 10,000 feet. But if we spin this around and have a look in our density altitude window, you can see that our density altitude is actually slightly higher than 10,000 feet. This arrow is pointing to about 10.5 to 11,000 feet, which is what you would expect because the air is warmer than the international standard. What else have we got? Over here we've got this window called Comp Core. This is what we call the compressibility correction window, and the compressibility correction window allows you to calculate, well, obviously compressibility correction. That is something to do with the fact that when you're flying, an aeroplane measures airspeed by measuring the amount of dynamic pressure going through the pitot tube, which is measured either through analog devices or digital devices depending on the type of aircraft. And it measures the airspeed based on the amount of dynamic air pressure physically pushing on some kind of sensitive membrane, which converts pressure into airspeed. Obviously, the faster you're going, the higher the dynamic pressure will be. However, above usually about 300 knots, you end up with something called compressibility, which means that the air starts to get bunched up in front of the pitot tube to such an extent that you actually start to get over readings. So you end up actually over reading your airspeed. So when you work out a TAS on the outer scale, if you end up with a true airspeed of greater than 300 knots, you can use this window here using a scale, which you can just start to see become visible there. Using this equation, TAS divided by 100 minus 3 divisions, as I'll show you in another video. And what you can do on here is basically correct the true airspeed for the effects of compressibility. What else can it do? Now this arc here, this pink looking arc, now on an actual CRP-5, I think this is blue. This blue circle is yellow on a real CRP-5, and this pink arc here is actually blue, I think, from memory. What this allows you to do is, as you can see here, we've got knots on the outer scale, 200 all the way up to 1,000 knots, and on the inner scale we've got something called temperature rise, and this is to do with something we call ram rise, or kinetic heating. And this is simply the fact that as you're flying, air is passing over the aircraft at very high speeds, and as a result of friction, the air is warmed up. And because the air is warmed, it is artificially heated. It is it also because air density depends upon the temperature of the air, the speeds that are calculated are going to be affected because of the increase in temperature, plus the fact that the instruments that are doing the measuring are heated themselves to prevent them from being iced over. And as a result, you can use this device here to tell you specifically what the temperature rise is as a function of airspeed. So again, let's say 300 and what's that, 20, 40, 60, 80, 100, so 320 knots, you can see there's an artificial temperature rise due to kinetic heating of about 10 degrees Celsius, which you have to take into account along with compressibility correction if required. What else do we have? On top of the standard printed items that are on here, you can also use a CRP-5 as a calculator. You can use it to do multiplication, division, you can do ratios, you can do fractions. There's a number of things you can do with it. It really is a wonderful piece of kit, and knowing how to use this thing inside out is one of the most useful things that you'll learn to do. on your ground school studies or as part of your PPL training. Definitely something that shouldn't be ignored. A lot of people tend to ignore this and try to use calculators for everything because it's just what they're familiar with. But this piece of kit does absolutely everything you could ever want it to do. So I think I've covered all the main parts, and as I say, over the next couple of months I hope to do lots and lots of individual videos with worked examples on how to use every single part of this device, both this side and on the wind side, using both the high speed and the low speed slide to enable you to work out everything you could possibly need to know to do with many forms of navigation, flight planning, instrumentation, and all the other subjects that you'll require. Any questions, anything you'd like me to talk about, anything you'd like me to discuss specifically, help yourself, put it in the comments, let me know, and I'll get back and make some more videos soon. Thanks for watching.